Welcome to this lecture on data compression. This is a supplemental lecture designed to cover some of the topics that I was not able to do in the regular classes. This won't be a very technical video. I'll mainly cover some of the nuances, some of the small aspects of compression, of real world compression. So let's go on with it. Alright, so recall that the problem of data compression is the following. We have a source file consisting of n symbols, and our goal is to save space. So the goal is to come up with an algorithm which is called a compression algorithm. So the compression algorithm takes as input the raw file and gives as output the compressed file, or sometimes called the code word. And the map from the source file to the compressed file is called an encoder or a compressor. And hopefully, so the compressed file is basically a sequence of k bits, and from the compressed file we want to get some reconstructed version of the raw file. After all, it has to contain some information about the raw file, otherwise it's useless. So the decompressor or the decoder is going to be another function or another algorithm which takes as input the compressed file and gives a reconstructed version of the source file. Now, depending on the relationship between x and xn hat, we can classify the types of compressors into two broad categories. One is the so-called lossless compressor, and the other is a lossy compressor. So lossless compressor is one wherein we want xn hat to be equal to xn exactly, or with very high probability we want xn hat to be equal to xn. So examples of lossless compression in practice are the sort of text compression and other file compression algorithms you see, such as zip or 7z or gzip and so on. So these are examples of lossless compression algorithms. So if you take a text file and run the zip algorithm on it, then you can unzip it and get back the original text file. There is absolutely no difference between the original file and the reconstructed file. On the other hand, sometimes we don't really want the original file exactly. It's enough to get some approximate version of this. So a classic example is JPEG. Right? So that's a lossy compression format where you have, say, a very high resolution image, and you want to compress the size. So you decide to reduce the resolution of the image, but at the same time it has to be the same image, right? We don't want it to look completely different. So this is an example of a lossy compression algorithm. Other examples of lossy compression are, of course, the various image formats like JPG, PNG, and so on, but also audio compression formats such as MP3 or various other formats. Same holds even for video formats. So MP4, FLV, all of these are lossy compression formats, right? So the lossy compression is also sometimes called quantization. So in the literature, this comes under the class of quantization algorithms. And typically, unlike lossless compression, where we want xn to be equal to xn hat exactly or with high probability, in lossy compression or in quantization, it's enough if the sort of the distortion between xn and xn hat is less than or equal to some fixed parameter. So for example, if we had, say, a binary sequence, a lossy compression algorithm would be one where maybe the number of ones, or say the number of bits in which xn differs from xn hat is less than or equal to some constant times delta, right? So So these are so the quality of a lossy compressor is usually specified by this function called the distortion function. One example of a distortion function is the fraction of bits which differ between xn and xn hat. But there are various other more complicated distortion functions that one could use. So for example, if you're looking at image compression, the number of bits in which the original image differs from the real image, or from the compressed image, that may not be a good measure of distortion, because the distortion measure needs to be chosen depending on the application in hand. So when we take two images, we want these images to be visually similar in some fashion, and so it turns out that using slightly more complicated functions, more complicated distortion functions, usually yields a better result. What this course and maybe the course on source coding, the upcoming course on source coding, so what these deal with are basically lossless compression algorithms, and lossless compression algorithms are broadly classified into two types: fixed length compression and variable length compression. So in fixed length compression, the length of the compressed file is a function of the size of the compressed file and the distribution, right? And this distribution, so we assume that the source file or the raw file is a random sequence, and this comes according, and this is drawn from some distribution px. Typically we will assume that this is an IID sequence drawn according to px, and to simplify things in this course, we will assume that this input distribution is known both to the encoder and decoder. So this is some extra information that we assume somehow we are given this knowledge, right? So in fixed length compression, the size of the compressed file is a deterministic quantity and depends only on n and px, not on the realization, not on xn itself, right? So in fixed length compression, we usually are allowed to tolerate a small probability of error, which is the probability that xn hat is not equal to xn, and we say that a lossless compressor is good, so a fixed length compressor is good if the probability of error, that is the probability that xn is not equal to xn hat, this vanishes with n. So as n tends to infinity, the probability of error tends to 0, right? So the game is to design an encoder and decoder such that k over n, the rate k over n, is as small as possible, and the probability of error vanishes with n. Now in contrast, what we see in practice are variable length compressors. So zip, 7-zip and gzip, all of these are examples of variable length compression algorithms, and here the size of the compressed file depends not just on n and px, but on the realization itself. So it depends on xn. So this implies that the size of the compressed file is a random variable whose distribution is governed by xn. Right? And in this, and for variable length compressors, we typically demand that xn hat should be exactly equal to xn. So we cannot tolerate any error, and this is most commonly seen in practice. So these were some examples and broad classifications of compression algorithms. Now it's not enough to just minimize the probability of error and the rate in practice. So in practice, there are other factors that come into play, and the most important factors which determines whether a compression algorithm is good or not, whether it's used widely in practice or not, is how easy is it to compress and decompress, or in other words, what is the computational complexity of compression and decompression, right? So as we've seen in class, the optimal rate of with which we can compress, the minimum rate of compression that one can possibly achieve, is equal to the entropy. So it's actually equal to the entropy rate. So the asymptotic rate of compression is the entropy rate defined as the limit as n tends to infinity of the entropy of Pxn divided by n. Right? So this is the best possible rate that we can possibly hope to achieve. And indeed there are good compressors, there are compressors known in practice, so there are very good algorithms which actually let you achieve this rate asymptotically. But again, a good compressor is one which not only achieves a small compression rate, so it not only achieves the entropy rate, but is also efficient in practice. So the natural question is, how do we encode and decode practically? Right? The simplest encoding method, or the simplest encoding function one could think of, is to design a table. Right? So you list all possible sequences, so xn of 1, xn of 2, and so on. So list all possible sequences, and for each sequence you assign a code word and you store this in the form of a table. And so on, right? So you maintain this enormous table of all possible sequences and the code words corresponding to each sequence. What does the encoder do? Once it receives an input file, it goes through this table and finds out what is the code word corresponding to it and outputs that code word. The decoder does the reverse. It goes through the table, it goes through the second column of the table, sees which code word has been received, and then outputs the corresponding sequence. So this is nice, but then it's very inefficient. You need to maintain a table for each xn. You need to maintain a separate table for each probability distribution, and clearly this is impractical, right? And so the goal is to come up with more efficient algorithms, and one class of fixed length compressors which turn out to achieve a very good rate are linear compressors. So one example of a linear compressor is, so basically, if you could do the following. So given xn, if you could just take a linear transformation of xn, a times xn, where this a is a k by n matrix, right? So you just multiply with a rectangular matrix, and this gives you your code word. Okay, so it turns out that you can indeed construct fixed length compressors achieving a small probability of error corresponding to each px. So this works for IID sources, but for more complicated sources it's difficult. And secondly, you need to construct a different matrix A for each probability distribution. So it doesn't work for all possible probability distributions. So practical compressors use more complicated functions, and these are not like just looking through a table or taking linear functions. Okay. So I'll get to the point of discussing how practical compressors work in just about a second. But before that, I'd like to revisit some of the assumptions that we made in the class. Right? So two assumptions that we made were the following: that encoder and decoder know px, right? And the second assumption was this assumption that the sequence is IID. right? So how do we, in practice, how do we remove these assumptions? So one way, if you have a large enough file, one way is to estimate px, right? And how do you do that? Now, given, let's assume that the input file is binary. Okay, so it's binary. It is we can model a binary sequence as a Bernoulli P sequence. Right? So assume that the raw file is a Bernoulli P sequence of large enough size. What we can do is, now a Bernoulli sequence is completely specified by the parameter P. So as long as you know P, you're done. And how do we estimate P? You just count the fraction of ones in the sequence, and that gives you an estimate of P. It's a reasonable estimate as long as the length of the sequence is large enough. And you can do this for any sequence or any alphabet. So if you have, let's say, an English text, then you can count the fraction of A's, the fraction of B's, the fraction of C's, and so on, fraction of each letter in the alphabet, and this is an estimate of px, right? So you estimate px. Now I'm still assuming that the sequence is IID. So you first estimate px, and depending on which px you get, the encoder chooses the appropriate function, the appropriate compression algorithm to use, and then it outputs not just the code word but also the estimate. So note that the decoder does not know px, so you somehow have to convey px to the decoder. If px hat denotes the estimate of px, then the compressed file basically consists of two parts. The first part consists of px hat, and the second part consists of the compressed sequence itself. So what does the decoder do? The decoder first reads px hat. Now it knows the distribution, and depending on which px hat was used, it decodes ck to get xn hat. So this works reasonably well. You can prove that even with this sort of estimation, for n, as long as n tends to infinity, you can still achieve the entropy. So you can still achieve optimal compression rates even without the encoder and the decoder knowing px a priori. Now note that the size of the compressed file is slightly enlarged because you also have to store px hat, not just ck, but this overhead is not too much, and since we are only interested in the rate, which is k over n, the additional overhead because of storing px hat is something very small. It is sublinear, and therefore it's a small quantity which vanishes to zero as n tends to infinity. So all of this works as long as the sequence is IID. But in practice, we don't really encounter IID sequences because so if you take English text, you can't really model English text as a sequence of IID characters. If you take a sequence of IID English characters, all you would get is rubbish. Right? So in practice, a more reasonable model is to use a Markov chain of a high enough order. So a better model is Markov chain. And indeed, many of the practical algorithms do work sort of based on these assumptions, based on the assumption that it is a Markov chain. And just as we develop a theory of information theory for IID sequences, similar results can be derived for Markov chains. And it turns out that the optimal rate of compression for any Markov chain, not just Markov chains, in fact for any stationary and ergodic sequence, as long as the input file is stationary and ergodic, so it's drawn from some distribution which is stationary and ergodic, the minimum achievable rate always remains the same. The minimum rate of compression is always equal to the entropy rate, which is h of xn, which is a limit as n tends to infinity of h of xn by n. Okay, and for the case and for the specific case where we have an IID sequence, the entropy rate just turns out to be the standard entropy. So all of this is still sort of more theoretical, right? We're still assuming a mathematical model, a probabilistic model for the source, and based on that we're designing these compression algorithms. But how do practical algorithms work, right? Now practical algorithms don't assume that the sequence is IID, and certainly algorithms of this form don't really work. So you can't maintain a table, you can't use different linear functions for each distribution. So practical algorithms, most practical compression algorithms use a combination of the following tools. So when I say practical algorithms, I'm still talking about lossless compression. Okay. Now, the sort of main concepts used in most practical compression algorithms, including zip, gzip, and so on, are the so-called Lempel-Ziv compressors. Lempel-Ziv algorithms, Huffman coding, and the Burrows-Wheeler transform. So what is Lempel-Ziv algorithm? Okay, so there's one more concepts that used. So it's not just Huffman algorithm. Sometimes some algorithms use arithmetic codes. Okay, so what is again, I won't describe the fine details of each of these algorithms. You can just look up Wikipedia or search online for these. But at a very high level, what do these algorithms do? What do these pieces do on their own? So the Lempel-Ziv algorithm turns out to be an optimal compression algorithm for any Markov source. So for any stationary and ergodic source, it's an algorithm which achieves the entropy rate. And how the Lempel-Ziv the nice feature about Lempel-Ziv algorithm, it's actually two algorithms, LZ77 and LZ78. So these are two algorithms named after their creators, Abraham Lempel and Jacob Ziv. They gave two different algorithms, one in 1977 and one in 1978, and these two algorithms are named after them, after these two papers, LZ77 and LZ78, and these are very widely used in practice. The nice feature about Lempel-Ziv algorithms is that they do not require you to know the input distribution. So it's an algorithm which is completely oblivious to the input distribution. It basically works on sequences, and it is always guaranteed to achieve the entropy rate of the sequence. And at a very high level, the way it works is the following. Now, if you recall the optimal compression algorithm that we saw in class, so the optimal compression algorithm worked in the following way. For each, so you listed sequences in some particular order and then maintained a table corresponding to each sequence. You assigned a code word, right? Now the problem with, as I mentioned earlier, the problem with having such a table is that you need to maintain a different table for each distribution and for each n. and you'll need to do this beforehand, right? So the table completely specifies the encoding and decoding algorithm. What the Lempel-Ziv algorithm does in very heuristic terms is that it tries to construct this table on the fly. Right? So you observe a long sequence. So initially you start with an empty table. So initially the table is completely empty, and you observe the sequence x1, x2, x3, so on, all the way up to xn. So what the Lempel-Ziv algorithm does is it tries to, so as you go through the sequence, you try to keep building this table in some fashion. So this table itself is completely determined by the sequence, and basically what you do is you go through, you start going from x1 all the way up to xn. You start with an empty table. As you go on from x1, x2, x3, and so on, you encode maybe x1, then x2, x3, and so on, and for each you assign a particular code word sequence, and the code word sequence at some point, say in the future, is completely determined on how you assigned code words to subsequences in this for the symbols preceding this, right? So while the compression algorithms that we studied in class were completely governed, so the code words were fully governed by the distribution px. So given n and px, you would know exactly what this table would look like. For the Lempel-Ziv algorithm, you construct this table depending on xn. So if you interchange the order of symbols in xn, you would get a completely different code word, right? And one sort of observation that the Lempel-Ziv algorithm is based on is that if the sequence has memory, so if there's so since it's a random sequence, when you look sufficiently far into the sequence, maybe somewhere over here, if you take a subsequence over here, now since the sequence is random, if you take any subsequence, with very high probability you will have observed this subsequence somewhere in the past, right? So you have a long enough subsequence, since the alphabet size is small, and if n is really large, then there are going to be many repeats, right? So take any subsequence over here, this subsequence is going to be repeated somewhere in the future, and these two basic ideas, one that you have a lot of repeats in the subsequence and that you can construct this table on the fly, these two are the very high level ideas in the Lempel-Ziv algorithms. Now the Huffman and the arithmetic codes are optimal compression algorithms or near optimal compression algorithms for IID sequences, and these algorithms, the Huffman algorithm and the arithmetic codes, are not used in isolation. They're usually used along with the Lempel-Ziv algorithm. So practical algorithms like ZIP don't just use only Lempel-Ziv or only the Huffman algorithm or only arithmetic codes. They use a combination of various things. You do a lot of pre-processing, and then you use the Lempel-Ziv algorithm, and to store some parts of the sequence you use Huffman or arithmetic codes. And Huffman codes are variable length compression. So both Huffman codes and arithmetic codes are variable length compression algorithms, mainly designed for IID sequences, and both are known to get very close to the entropy. Now the Lempel-Ziv, Huffman and arithmetic codes are compression algorithms designed specifically for compression. But in contrast, the Burrows-Wheeler algorithm is not a compression algorithm in itself, although adaptations of the Burrows-Wheeler algorithm for compression have been studied. The Burrows-Wheeler algorithm is more sort of a pre-processing algorithm. what it does is, if you give any input sequence to the Burrows-Wheeler algorithm, then it outputs another sequence. So it's a biject. So the Burrows-Wheeler algorithm is basically a bijective function, but what it tries to do is sort of increase the number of zeros and ones which appear in succession. So if you have a sequence where the characters are all over the place, maybe A, B, C, A, B, A, B, C, D, E, then it somehow tries to, then the Burrows-Wheeler algorithm basically gives you a permutation of these letters such that the A's are all maybe close together, the B's are all close together, the C's are all close together, and so on. So again, this is completely hypothetical, but maybe what the Burrows-Wheeler algorithm might do would be give output maybe A, B, B, C, B, A, D, E. So it tries to group similar characters close to each other. It's a lossless algorithm, so there is absolutely no loss of information in the Burrows-Wheeler algorithm. So as I mentioned, this is sort of a pre-processing step, and the main usage of the Burrows-Wheeler algorithm. So why do we do this pre-processing? We do it so that Lempel-Ziv can compress the sequence better. So if similar symbols are close to each other, then it implies that the Lempel-Ziv algorithm can compress the sequence better. Right. So these were some high-level aspects of compression algorithms used in theory and in practice. So to summarize, we saw that compression algorithms can be broadly classified into lossless and lossy compression, and this course will mainly be seeing lossless compression algorithms. We saw some aspects of encoding and decoding, and how some assumptions that we typically make in class can be relaxed, and I gave a very high level overview of how practical algorithms work. Now, data compression is a complete subject in itself, and we won't have time to cover more aspects of this in class. Some of these will be covered in a successive course on source coding, but even there we won't be able to cover everything that is known about data compression.